Hello everybody, welcome. My name is Fala. We're going to talk about some basic logic circuits. This is a beginner's level course, so I apologize if it's a little too remedial, but hopefully we'll cover some interesting things. So, what is a logic circuit as opposed to, say, a different type of electronic circuit? So like an audio amplifier, for example, is not a logic circuit. An audio amplifier would transmit a signal that is changing and varying over time, like the sound of my voice is vibrations over time in a wave form. Logic circuits are on and off, 1 and 0, true or false. And because that, there are analog computers, but most of the computers that we see nowadays are digital. At some point in history, that just became the best way to make computers, so that's what they are. So how does logic work in a computer? Well, with 1s and 0s, because a computer is going to turn something either on or off. So if I'm counting to 10, I have 10 digits to deal with, but if something's on or off, you only have 2 to deal with, 0 or 1. So we use the binary number system. So for example, the number 0 would be represented as all zeros, the number 1 would be a 1, and then you see this place in the decimal system, this would be a 10, but we only have 1s and 2s, or 0s and 1s here, so the 2 would be in this position. The 4 is that place, the 8th place, 16th place, 32, 64, 128, and then just to show like what happens, the most you can represent with 8 bits is 255. Each one of these digits is called a bit, and then you add 1 to that, everything rolls over, and that's 256. There's 1 with 8 zeros after it. And so this would be, if you want to, as many numbers, decimal numbers as you can count with 4 bits, is 0 through 15. As you can see there, 1, 2, and then 2 and 1 is 3, 4, 4 and 1 is 5, 4 and 2, 4, 2 and 1 is 7, and so on. Now, to work with those 1s and 0s, those ons and offs, computers have what's called gates. They're circuits that can take different inputs and provide an output based on the function of the gate. So some of the functions are, say, an AND gate or gate not gate. An AND gate would take both inputs and look at both inputs and say if both of them are on, then the output is on. If either of the inputs is off, then the output is off. An OR gate would say if either of the inputs or both of the inputs is on, then the output is on. If both of the inputs are off, then only in that case would the output be off. A NOT gate is just an inverter, and you'll see how that's useful later on, but basically that says the input, the output is just the opposite of whatever the input is. So, how can we build some of these with circuits? A transistor, if you're not familiar, is an electronic switch. That's one use of a transistor. It can also be used for amplification, but we're talking about 1s and 0s, so we're only going to be talking about it as using it as a switch. So in this circuit, we have a battery over here that's producing 5 volts, and it goes through a resistor and a switch to the base of this transistor, and then the emitter of the transistor goes to ground, and the collector of the transistor goes through an LED through a resistor to 5 volts. Now, how a transistor works is if you have current through the base and the emitter, then that turns the transistor on so that you have current through the collector and the emitter. If there's no base emitter current, then the collector emitter current is shut off. And in this case, this is an NPN transistor, and that's a little beyond what we're going to talk about here, but what we need to know is the current needs to go in this direction. The conventional current flow would go from the base to the emitter, so positive to negative. So in this case, if you push the switch here, and you have a positive voltage flowing down here, this is more positive than the emitter, so you have a positive current flow from the base to the emitter, and when that happens, then the collector emitter current starts to flow, and the LED comes on. So this is a circuit on the breadboard. If you push that switch, this is this exact circuit built up on the breadboard. You push that button, the LED comes on. And you might say, well, who cares? I can put a button directly on an LED and it'll do the same thing. Well, I'm not going to be inside the computer pushing buttons. So what we need the transistor for is so that you can electrically switch the circuit instead of mechanically switching it with a button. And that's where the transistor comes into play. This is the opposite of what we just saw. So this would be when you push the button, the transistor goes off. In this case, so this would be an inverter or a NOT gate. So 0 would be 1 and 1 would be 0. So if the button is off, then there's no base emitter current, so there's no collector emitter current. And so this transistor is off. And if this transistor is off, then this part of the circuit doesn't exist. But this part of the circuit lets the LED come on. You push the button, and the transistor has current flow from the base to the emitter, and this is now connected. It's basically shorting across the LED, and so the LED goes off. So this would be the opposite of the last circuit, where the button turn it on the other one, and turns it off on this one. This is another illustration of a NOT gate or an inverter. Whatever voltage you have 0 volts on the input, you're going to have 5 volts on the output, assuming that this is going to 5 volts. We're going to probably talk about 0 to 5 volts because that's a very common voltage with computer circuits. So if there is 5 volts here, that turns this transistor on. And so then this will basically be connected from this point to this point, collected to emitter. And so the output will be ground. So this is on, this is off. This is off, this is on. Here are some other gates represented in the transistor circuits. This is the AND gate, where we talked about if both of the inputs are on and the output's on. And the OR gate, if either of the inputs is on or both and the output's off, output's on rather. So if these two are on, both these transistors are on, and only then will this LED be on. If one or the other of these transistors on, that's completing the circuit so that the LED is on, and versus OR. Any questions about anything at this point?
How do you determine the minimum current needed to turn on a transistor?
That's a little beyond the scope of this talk, but basically,
Read the data sheet.
read the data sheet. The data sheet of transistor, but for switching transistors, we're not operating the transistor in its quiescent mode, which means the varying voltage mode. So it can change. That's how an amplifier would work. You could make a wave. The input wave would be amplified in the output wave. And we want to put a voltage on the input and just have it go all the way on, or take that voltage away and go all the way off. So that's what operate either in cutoff or saturation. In that case, all you need to do, typically, the base emitter voltage is around 0.6 for a PN junction. And that's beyond the scope of this talk. But if you overcome, so basically if you hit 0.7 volts on the base to ground on the emitter, it's going to turn that transistor on. Okay, thanks. And a better illustration of an AND gate, your inputs, both of them have to be on, so both transistors go on to make the output on. If either one of these is off, this part of the circuit is open, and therefore your negative voltage, or negative 0 volts rather, would be connected to the output through this resistor. If these two are on, that's basically going to be a short for all intents and purposes. so your supply voltage would be at the output. There's an OR gate similar to the other, actually it's exactly the same, just a better drawing. If either one of these transistors is on, then the supply voltage is going to the output. If both of those are off, then the output is grounded. Now, this is an exclusive OR gate, which comes into play later on. We'll show you a very useful gate. The OR gate, if one or the other, or both, inputs are on, the output's on. Exclusive OR, exclusive being the key word, says we're only going to exclusively look at one input. If both of them are on, then the output's still off. So if only B is on, output's on. If only A is on, the output's on. But if both are on or both are off, the output's off. And so this is a fairly complicated circuit to accomplish that. We have to use 5 transistors. So basically, A is connected to A there, B is connected to B there, so it's the same input. So if A and B are on, then this part of the circuit's on. And then if this is on, then that grounds the base, and this transistor is off. If this transistor is off, then this circuit is also basically non-functional because we would need current flow from supply to ground for these transistors to do anything. So both of them are on, this disables the circuit. If both of them are off, then this whole circuit would be off anyway, so the LD would be off there. But if one of them is on, if this just the A is on, this is not doing anything. So then this transistor would be on because we've got base emitter current. And one of these would be on. So since this is on, then, so let's say A is on, there's base emitter current because this is on, and then the LED comes on. So there's a transistor representation of an exclusive OR gate. And these are a lot of the gates that we talked about, plus a few extras. So buffer is just whatever's on the input is on the output, and it may not seem interesting, but if you've got a lot of circuits to drive with a low current signal, then a buffer is handy for that. And there's other reasons why you use a buffer. An inverter takes the input and gives you the opposite of the output. And an OR, we talked about both on, outputs on, either on, outputs on. Exclusive OR, if only one is on, the output's on. And then the exclusive NOR, the NOR and the NAND are exactly the same as these, except that the output is just reversed. So you can see 0, 0, 1, 1, 1, 0. 0, 1, 1, 1, 1, 0, 0, 0. And again, these come in, to have that inverted output is handy later on when we're building things. So to use these in real life, we have integrated circuits. Instead of building it up with transistors, we have all those transistors shoved into a tiny little package that's microscopic, but it has connections we can actually connect to and solder to. And a very basic, very common, like probably the first gate that everybody learns about is the 7400. In this case, 74 LS00 LS is low power transistors. That's Schottky. Low power Schottky, that's right. There it is. This is right there. So this is part of the data sheet, and here's some more interesting things on the data sheet. There's all your voltage ratings, and so we got input voltage, high and low voltage, input clamp, power supply, current, and all things you need to know to wire this chip up in a circuit. And it also shows you, if you want to connect this NAND gate, pins 12 and 13 are the inputs for this gate, and there's 11 is the output, and there's 4 of them in this one little package. So handy little chip, and these data sheets, they used to be in big books years ago. Now we have the internet. I used to have a lot of those books. They were very fun. Those were a long time ago. This is a better picture of the internal wiring of the 7400 NAND gate, quad NAND gate. Now, what can we build with these gates? So let's say I want to do some math. I want to build a computer that can add 2 numbers together. Well, I can take some gates and I can wire them together. So if I have 2 wires coming in, either one of them is either a 1 or a 0, on or off, then I can run those through some gates so that the output's going to say, okay, 1 plus 1 is 2, or 1 plus 0 is 1, or 0 plus 0 is 0. And so if A and B are 0, the sum is 0. If A or B is 1, the sum is 1. If A or B are both 1, then the sum is 0. But in binary, all we have is 0 and 1. So if I'm counting in decimal, I got 10 fingers. I got 0 through 9 digits that I can play with. In binary, excuse me, it carries over to the next column. So 1 plus 1 is 2, but in the 1's place, in my binary number system, that would be a 0, and that would carry over to the 2's place, so there'd be a 1 in the 2's place. So how the circuit works, this is actually an exclusive OR gate, but using simpler gates to produce it. So if A is 1, then it's inverted here, and so this would be a 0. So this AND gate would be off right away. But this AND gate would be, there'd be a 1 there. So now we have to look, say if B is 0, then that's what also, the output, this would be inverted, so that would be a 1. So if A is 1, B is 0, this is on, and so this is an OR gate over here. So if either one of these is on, then the output is a 1. If B is on, A is off. A is off, this would be a 1 here. This would be a 0, so that's 0. If, what did I say, B is 1, so that would be a 0. Wait a minute, what did I say? Oh yeah, B is a 1. Then this is a 0. A is a 0. Hang on a second. If B is a 1, then this is a 0, so that's off. But if B is a 1 and A is a 0, then this is a 1, this is a 1, so that's off. So there you go, so your sum is 1. This is only part of the adder circuit though, because we're not accounting for that carryover, and we're not accounting for a carry in. So this adds some extra circuitry so that we can say if A and B are both on, the sum would be 0 because 1 plus 1 is 2. We don't have room for a 2 in the first digit. So this carries over to the second digit. And A and B are both on, that carries on. This is a little bit better. This is an exclusive OR gate. So this took the place of a lot of that other circuitry. So if you think about it, if A is on or B is on, then the sum is 1. But if A and B are both on, that means it's carrying, so the sum would be 0, but if they're both on, then the carry would be 1. And so here's a full adder. So now we have circuitry for the carry in addition to the normal adding circuit. So basically it's doubling up on a lot of the circuitry. And let's look at this one, it's a lot simpler. So now we've got 2 exclusive OR gates, 2 AND gates and an OR gate there. Let's say A and B and carry in are all on. So A and B are on, this exclusive is off. Carry is on, so this one's on because this is off and this is on. So the sum is 1 because it's carry. And A and B are both on, so this AND is on, this OR would be on, and so the carry is also out on. Anybody have any questions about this? Look good? Okay, it's making sense.
Well, where does carry in come from?
Carry in would be, so this whole circuit is for one binary digit. So I can add 1 and 1 and that's it. So let's say I want to add bigger numbers. Well, I have a whole bunch of these that are chained together, actually, just like that. So what we just saw there, this whole string is inside one of these boxes. So we've got the A and B inputs. So this would be 1 digit, the next digit, the third digit, the fourth digit. So let's say we want to add 1, 1, 1, 1. to 1, 1, 1, 1, then you would get the sum of the individual digits plus the carry would ripple down. So from the ones place would ripple down to the 2s, from the 2s would ripple down to the 4, and then down to the 8. Okay. So let's talk about how we can use some of these gates. So this is a nice program. It's called Logic Circuit. It's a free download. I think if you Google it, you should be able to find it. And you can simulate some gates here. So here's a NAND gate. So I can already tell. Is that red?
Yeah.
Okay. So that's on because both inputs are off. If either input, oh wait a minute, now it's off, now it's on? Yeah, okay, I see it now. I'm a little colorblind, so it doesn't hurt, doesn't help. If both of these inputs are on, the output's off. If both of these inputs are on, the output's on. So the AND gate and the NAND gate, there's a little bubble there. It's hard to see on this simulator, but it's a little inverted output. These gates function exactly the same, except that the output is backwards. The OR gate, if either of the inputs is on, the output's on, or if both of the inputs is on, the output's on. Here's our exclusive OR. If one is on, the output's on. If the other is on, the output's on. But if both of them are on, the output is off. The inverter, just on is off is on. Okay? And here's the adder circuit. This is without carry. So 1 plus 0 is 1 with no carry. 1 plus 0 is 1 with no carry. 1 plus 1 is 0 with a carry. This is accounting for carry in and a carry out. So 1 plus 0 with a carry in would be 0 with a carry, so there's a 2. 1 plus 1 plus 1, so adding 2 digits, we also have a carry from the previous digit. So we get a 1. So 1 plus 1 plus 1 is 3. And if this is the 1's place and this is the 2's place, 2 plus 1 is 3. So there's your binary addition there. And all the other combinations work as well. Let's say I'm adding 0 plus 0, I have a carry, so then it's just 1. And now I'm going to take those, I want to add more than just 2. So everything on this screen is now inside one of these boxes. So if I want to add 1 plus 1, then it's 2. The output's 2. So the 1 and the 1 both go to this first stage. The output of this first stage would be a 0. It carries over to the second stage. The second stage says, okay, all I have is a carry. I don't have any other inputs, so my output is on. It is on. Yep. Okay. If I'm adding, let's say it's 5 plus 9. Let's see, 5 plus 9, we've got 8, 4, and 2 on, right? So that's 14. So math is right. So I got 16 plus 1 plus 4 plus 2 plus 8. All those are wrong. So that's easy. And I can also have, if I have this whole circuit and another one just like it, I can carry in from another group of these, and you can just go as long as you want. Now, something I just was playing around with last night, I thought it'd be fun to show. It's a little bit, if you don't know what 2's complement is, it's how you do subtraction in binary. And basically, when you're subtracting, you take the 2's complement of the second number, you invert all the bits, and then you add 1 to it. And it sounds weird, but when you take that second number and you do the 2's complement of it, you add the 2 numbers together, you get the subtraction of the 2 numbers. And you just would ignore the overflow bit. So right now, it's just an adder. So like 4 plus 4 is 8, so there is the 8 is on. But let's say I go 8, so that's 12 minus 4. Oh wait, 12 minus 4 should be 8. I'm going to turn the subtract button on. And so the 32, the rollover, we ignore because the 2's complement causes that. But then the answer is 8. 8 minus 12 minus 4 is 8. How we're accomplishing it with one little switch here is to invert all these inputs and then add 1. This little subtract button is connected to the carry in. That's where we're getting the add 1. And then it's also going to one input of these exclusive OR gates. So if the input is going to one input of the exclusive OR, and the subtract selector is going to the other input of the exclusive OR, we can see that what happens with an exclusive OR. So let's say we, this isn't drawn very hard. So let's just say that our input is B and our selector switch is A. So if we want the number itself, then B is on the output. So this is our number we're passing it through, we're adding, we're not inverting. And this is B is 1, the output is 1. But if we turn on our subtraction switch, then here our subtraction switch is on, so the input is going to be inverted, and the input there, 1 is going to be a 0, 0 is going to be a 1. So an exclusive OR is a very handy little circuit that we can use to invert, to just have one little selector line and invert our binary number. So, and I just threw this together in like 5 minutes, so I apologize for the crisscrossing lines here. Now, so that's addition, subtraction. That's how a computer can do this, basic, very, very basic level how a computer can do math. Let's say we want to store some information. So we can hook up some gates in a crisscross pattern like this, so the output's going back to the input. So if I set this gate, the output, which is Q, this is Q, this is the inverse of the output. It has a line under it, so it's a line over it, but I didn't have a way to draw that. If I click this input, the output's on. So I've set this bit. Let's say this is 1 bit of the number. I've set this bit and it's on. Now, if I keep setting it, it's not going to change. Only when I hit the reset input does that go off, and then this would be the inverse. We can ignore that, in fact. Let's just do that. Let's ignore that. All right, so if I set this gate, I set this latch, I can set it all day, it's not going to change. And it's going to stay set until I hit reset, then it goes off. Now let's say I want this to be in a bigger circuit where I want better control over it. I want to be able to have other circuits driving it. I can wire up these AND gates on the input in this inverter so that I'm doing this set and reset with a single button, but I have an enable to either make it work or make it ignore the input. So if I set the input here, actually let's enable it and let's. Alright, so now the output is off. So now I disable it, okay? And now let's say this is connected to a bunch of other things in the circuit somewhere, and this data is changing. Well, it's not affecting the output because it's not enabled, the circuit's not enabled. So this is a good way to say, alright, I want to store a 1, and there's my 1. And then this data line is going somewhere else. It's busy with other tasks. It's not affecting that. And this is called an SR latch, set reset latch. This is a D latch. Now let's say I want to do just a lot more of this. I need to connect this to a clock so that my input's only changing when the clock goes positive. And if you'll see later how that makes a difference. But if you're connecting like a memory circuit inside a computer, you want it to only react when that particular circuit is active and only on a clock pulse, so that your timing between different circuits doesn't conflict. So this clock is going on and off every second. There's a clock. Okay? And so if I set this, the output's on. And I don't know if you can tell, but that output only went on the rising edge of the clock. So when the clock goes positive, the output goes positive. So now, I turned off the input, but there's no reset on the K, so the output's still on. So when I turn off, I reset the circuit, so I want to make my output a 0. On the next rising clock pulse, the output goes off. And how this, so here's our basic latch that we saw at the beginning. This is our enable circuit, all right? And the enable circuit is inverted, is the clock inverted. And then the clock not inverted also goes to another whole set of these latches. All that circuitry is there to ensure that you only get a change on the positive clock pulse, and it doesn't change otherwise. Now, let's say I want to have what's called a register in a computer. Register is basically one little memory location that stores a value. This is only a 1-bit register. It's only going to store 1 or 0. This box here contains everything we saw in the last circuit. All right, so what we're doing here on this register is, I have a clock here, but I also have a button, so I can just do it in 1 clock cycle. So let's say I want to load a 1 into this register. And is that on? Okay, yeah, that's on. Now I'm going to disable the load button. All right, so if the clock is continuing to run with data on the input, we still have the 1 stored in that register. Okay, only when the load is active and the clock cycles does the value of that register change. And how we're doing that is, this is the set input on the flip-flop, or the latch. And this is the clock input on the latch. And so, if we are loading, or let's say we're loading data. We're loading a 1. So, the load is inverted, so this AND gate is off. And if this AND gate is off, then anything coming from the output is not going to do anything. So this OR gate is only going to get information from this AND gate. And this AND gate is going to get information because this is enabled with this input, and so whatever's on this input is going to get sent through. So if this is off, this is on, and this is off, so then this is off. So an AND gate, basically this is enabling this data to pass through. If I turn this off, this AND gate's disabled, so this data doesn't go anywhere past this point. It's shut off by the AND gate. And the input to the flip-flop is going to be whichever one of these is true. Now, if load is off, we're not loading data, then whatever data is in, so as the clock is cycling, it's actually reloading the same data back in to the circuit during every clock pulse. Until we turn load, then it's going to load what's on the data input. So that's only 1 or 0, that's not very helpful. Let's see what a bunch of them do. So here's a whole bunch of them. And what we saw on the last screen is in one of these boxes. And so we've got all the load inputs tied together, we've got the clock running, and then we've got 8 inputs. So let's say load is just a momentary button this time. All the inputs are off, so all the contents are off. So let's turn on a few bits here. All right, this is still off because we haven't enabled the load. So if I hit the load on the rising clock pulse, nothing happened, or did it? Okay, it did happen, it was fast. Let's turn those back off. So if I hit the load really fast, I don't know if did I get off?
Yeah, they're off.
My clock is running at 1 cycle per second, so theoretically I could hit that input fast enough that the clock didn't pulse long enough to load that data. So now I'm loading. I loaded 1 0 1 0 1 1 1 0, and there it is. Now this data, these data lines can be changing, and the computer can be off doing other things. And as long as this load isn't active, this register maintains that value. Let's see how much further I went with this. I think that's about it. So, that's most of what I wanted to cover today. Does anybody have any questions? They want to try some other examples on this tool?
How big is the library of?
Actually, the library, if you download this, you don't have much. You have inverter, AND, NAND, OR, NOR, exclusive NOR, and a ROM and a RAM chip, which that's some things with it. You have input-output devices. So let's say I want to build some gates here into a circuit that I want to use elsewhere. I can tag them with this input notations and the output notations, and then that will create this little box with these little connections on it. Then I can then drag this and use it and wire up stuff to it. And then you can put more labels and drag that somewhere else, and you can keep building until you have modules built up. Well, what comes with it is just basic input-output tags, push button or a toggle switch, a static value, either 1 or 0 in either 1 or more bits, and a clock input, a pin splitter here. This is cool. So let's say this connection on this circuit really has 8 wires attached to it. So then I can use one of these, and I can connect this over there, and then that's really going to have this. This can't be a mismatch. If it was, when I go to run it, it would give me an error. But I can make this. Let's say this was 8. I can say 8, and then there's one with 8.
You said this is a free download?
Yes.
Oh, nice.
And can you save these things that you create into the?
Yes. Well, see, that's the other thing. So there are a couple examples that are online, and then there's some things that I built. So you can import projects from, like some of these up here. These are the ones I built at the top. But some of these are from other circuits that were imported. So like here's a calculator. So I haven't played with this, so I apologize if this doesn't work. So 1 plus 2 equals well, this is some example that it came with. All right, I downloaded it, imported it into this. But that's how you can add other circuits that somebody else designed, and then you can use them. So let's say, I don't know what this is. let me show you one more circuit. So, something that is used in a lot of computers, and if you're working with Arduinos and other type of hobby circuits, you might use a shift register because you only have 1 or 2 pins and you need more than that. So how a shift register works is you can cycle in your data, 1, 0, 0, 1, 0, whatever you need, and it will distribute that across multiple outputs. So each one of these has a circuit that latches the data bit and then ripples it down to the next data bit. So how that would work is let's say I want the number 10101010, but I've only got a few pins coming out of my Arduino or my computer, my vintage computer, my Commodore, or something like that. So every clock advances to the next bit. So let's say I have 1 clock, 0 clock, 1 clock, 0 clock, 1 clock, 0 clock. Now I don't see anything on the output because I have to enable it. So then I hit my store button and did it make a liar out of me?
No, you need the output enabled too.
Yeah, sorry about that. Thank you. So we turn this on, and there it is. So we should have, I can't tell. Is it 1010 1010?
No.
This one.
Is this one on? No. And this one's off? Alright, so let's reset and store that. So everything's off, right?
Yep.
So I go 1, clock it in. 0, clock it in. 3, 4, 5, 6, 7, 8, and then store.
There you go.
There you go.
Alright. So it's called a shift register. Basically, one way of taking serial data and turning it into parallel data. Parallel means all 8 bits at once, serial data is 1 bit at a time. So that's another handy thing. A lot of the inspiration for these circuits came from a YouTube channel that I saw. Whoops. A guy built a computer in a very basic sense of the word on a breadboard, and he built the registers by with individual chips, and the processor isn't even a processor. He has his instructions like determined by ROM chips, and all his internal enable logic it's really a brilliant series. There's probably 20 or 30 videos. I really recommend watching this guy's YouTube channel. His name is Ben Eater. Interesting name. And he adds a lot more detail to the things that I just covered today. A lot of insight on how the internals of a computer function and things like that. Any other questions?
To tie into, I'm working on an S100 plus board.
I'm sorry.
Let's say I'm working on an S100 board.
Okay.
It's got a fairly dense logic circuit.
Right.
If I enter that into your software tool, or the software tool you just demonstrated,
Sure.
Does it have the capability of outputting a logic chart for troubleshooting or to follow the logic through the board in not to tie it into reverse engineering, but
I don't know that it would output specifically what you're looking for, but you would be able to simulate, if you entered all the gates into the simulator the way that the computer is assembled, the way the computer is built, then you could simulate and you could drill down into those components and say, if I've got data coming in over here, how's it reacting to these circuits over here?
so in parallel, troubleshoot the circuit and change the logic on the software side of it,
Right.
and make sure the results match.
Right, theoretically you could do that. That sounds like it would be very complex for something like this, but theoretically, yeah, absolutely, you should be able to do something like that.
What's the next level up? Maybe something that costs money.
Nothing that I've invested in. I'm sure there are a lot of commercial packages for guys that are designing, whole computers that do things like that.
Maybe something like LabVIEW or something.
Yeah. Yeah, I don't work in this, in the industry, so I don't know what's currently available. But yeah, I'm sure there are things beyond what I can imagine right now that would probably be several $1,000s or more for.
Well, I was wondering if there's something in the middle somewhere that.
There are probably some free programs for designing circuit boards that would incorporate some of this. I think, Eagle, I don't know how it is.
That's
these days.
simulation.
What's the
So,
number?
so for simulation, if you're talking about going to a larger scale, usually you start talking about hardware design languages like VHDL and Verilog, and there are free simulators for that, and they go all the way up to the tens and hundreds of thousands of dollars. Yeah,
There's
depending on
also-
your scale.
There are also really good cheap ones.
Yeah, I mean, and free.
ones. Yeah.
Icarus Verilog is good and easy to pick up. If you have
That's well, Verilator is a lot faster.
just 5-minute working list.
I'm good.
Oh.
Any other questions? I'm pretty much through the. Go ahead.
So if you're using 3.3 volts, would these 7400 chips still work? Or?
No, 7400 chips are very specifically 5 volts plus or minus a quarter volt. That's the rating on 7400 series logic chips. They are definitely 5 volt chips. Now there's some CMOS chips, 4000 series chips that have a wider, quite a bit wider range. I don't know the specific limitation for that, but it's. I don't know if it would go down as low as 3.3, but it'll definitely allow you to go to much higher voltages. I think up to like 17 volts or I forget.
And there's newer generations of CMOS chips that have adopted the 7400 numbering. So like if you get 74 LVC series, those are usually 3.3 and below.
Okay, so a newer generation that provides the same function but gives you
Right.
a lower voltage.
Look for the letters in the middle.
Yeah, I was wondering about, I think it was an SB prefix on the first or second slide that you had. You know, SB74 LS00. Yeah, SM.
SN, I think that's a manufacturer.
I think that's National Semiconductors prefix, but they sort of off, or TIs.
The important, there's 74 and the numbers. Ignore the letters. That's going to tell you what kind of gates they are, what kind of circuit it is. LS is, and other numbers, other letters in the characters are going to tell you what, how the circuitry is built. What types of transistors are used? Are they fast? Are they slow? Are they high current? Are they low current? Are they going to, are they heat up, or are they going to, run nice and cool? And then, yeah, some of the prefixes have to do with manufacturer. But mostly, like 7408 is another, say, I think it's like an inverter or an AND gate or something like that. You can Google these numbers, and in fact, I've typed some of these numbers where it'll be 74 and then 3 digits. And I think Google's going to come back with a zip code because it's 5 digits, but it knows what shit we're talking about. It finds it. So it's good. It's really handy. It sure beats paging through the giant books, although the books were a lot more fun. All right, guys. Thanks very much.
Thank you.